This video is on section 12.4, limits at infinity and limits of sequences. In this section, we will be talking about limits at infinity and infinite limits. So basically functions that extend forever in the x direction or y direction. And then we'll also talk about limits of rational functions. Basically, when we talk about limits at infinity, this basically means when a function extends forever to the right or forever to the left. And the way we denote that is by changing this x value. So basically, instead of saying x approaches a specific number, we're going to say x approaches infinity or negative infinity. So that just means the function extends forever and ever. So now we will have a function that could potentially be bounded by horizontal asymptotes or vertical asymptotes. But we've already talked about vertical asymptotes, so today we're going to talk about horizontal. So as x approaches positive infinity, the intended height of the function is 2. However, as x approaches negative infinity, the intended height of this function is -2. And that's illustrated right here. Now this slide is pretty busy. I understand that. And you know, this piece here, it has a lot going on. And so just kind of hear me out for a second. We're just talking about horizontal asymptotes. And remember, when we're finding horizontal asymptotes, these are the key pieces right here. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is just the ratio of the coefficients. Let me give you an example. If f of x is equal to 3x squared over 2x squared. And of course, there can be other things included in this polynomial, but the thing you want to notice is that these are the same. If these are the same, then the asymptote is y equals 3/2. And the reason it's nice to find the asymptote is because if there is a horizontal asymptote, then chances are the limit at infinity is the same thing. Now, if the degree of the numerator is less than the degree of the denominator, then we will have a horizontal asymptote at y equals 0. For example, if f of x is equal to 3x divided by 2x squared. Here, the denominator is bigger, and if you want to reduce this, you can. If you reduce this, this becomes 3 over 2x. Well, as x gets bigger and bigger and bigger and bigger, the denominator is getting bigger, and the numerator is remaining the same. So if the denominator gets bigger, like 3 over 20, 3 over 200, 3 over 2,000, 3 over 2 million, this is approaching 0. So the horizontal asymptote is 0. Finally, if the degree of the numerator is bigger than the degree of the denominator, for example, if I have f of x is equal to 3x squared over 2x, if I reduce this, this just becomes 3x. Well, here, there is no restriction on what we plug in for x, and the output is absolutely anything. It doesn't approach anything. So there's no horizontal asymptote in this case. Okay, now, again, it's important that we are able to identify horizontal asymptotes, because if we can find the horizontal asymptotes, then the limits at infinity are the same thing. Let's look at some examples. So here in example 1, it says find the limit or indicate that the limit does not exist. So if I look at these problems, really all I'm trying to do is see if there's a horizontal asymptote. when I look at this, there's only an x value in the denominator, which means I am simply going to be plugging in x values that get bigger and bigger and bigger in this denominator. So think about what's happening. Well, we can compare this to a function that has a horizontal asymptote at y equals 0. This function is going to be approaching 0. So there is a horizontal asymptote at y equals 0. So if there's a horizontal asymptote there, this limit is 0. In number 2, it may be helpful to rewrite this as a fraction so you can see what's happening. This can be written as the limit as x approaches negative infinity of 1 over x to the 4th. Okay, now this is very, very similar to the problem we had before. Okay, the only difference is we're going to be plugging in a negative value. Well, because we have an even exponent, anytime we plug in a negative, the output is positive. So as x approaches negative infinity, this is still approaching 0. There's still a horizontal asymptote at 0, and that's what our result is. In this one, if I have a negative exponent, I can move it up to the top and it becomes positive. So rewriting this, I have the limit as x approaches infinity of x to the 1/2 power. Recall, anytime you have a power of a half, that's the same thing as the square root. Oops, just the square root. Well, here, I want to plug in bigger and bigger numbers here. Nothing crazy is happening. So, in this case, there is no horizontal asymptote. If I plug in bigger and bigger and bigger numbers, this is just going to increase without bound. If our limit increase or our function increases without bound, then the limit does not exist. So the answer is does not exist. This here basically talks about limits, evaluating limits at infinity. We've already kind of addressed this. So let's look at some examples that are a little more complicated. Now looking at this, whenever I see a fraction within a fraction, instead of dealing with it as is, I personally think it's easier to eliminate that fraction within a fraction. So what I would do is I would multiply the top and the bottom by the least common denominator, which in this case is x squared. So I'm going to multiply the top and the bottom by x squared. When I do, this is 2x squared. When I multiply this, I end up with just minus x. In the bottom, this gives me an 8x squared, and this just cancels to a positive 1. Okay, now this seems a little more manageable. Now I just look at the largest exponent on the top and the bottom. Because these are the same, I know that I'm going to have a horizontal asymptote at this ratio. So that means the limit is the same thing, because as x gets bigger and bigger and bigger, the end behavior is the same. So this is equal to 2/8, which reduces to 1/4. And that's the final answer. Okay, and the next one, I'm just going to compare these, and I notice that the denominator is bigger. If the denominator is bigger, no matter what I plug in, the number can be infinitely big or infinitely small. The horizontal asymptote is still y equals 0, which means the limit is y equals 0. On the other hand, in this example here, the numerator is bigger. And if that's the case, there's no horizontal asymptote, and this limit does not exist. I can look at this graphically as well. So same problem, but now we're given a graph. And I'd like to mention that even though this viewing window is given to us here, this function extends forever up, but it also extends in the rightward direction also, slowly, but it will still go that way. And then in this direction here, we can kind of see that we're leveling off a little bit. Okay, so as x gets infinitely big, the intended height of this also increases. So as x gets bigger and bigger and bigger, so does y. So that means that f of x increases without bound. So this function is approaching positive infinity. Anytime a limit approaches positive or negative infinity, the intended height cannot be determined, so the limit does not exist. Now, on the other hand, as we approach negative infinity, so as x gets bigger and bigger and bigger, the intended height of this function is 5. So we can see here that these do not have to be the same. Here, we're just talking about limits of a sequence. And when we talk about limits of a sequence, it's basically the same type of thing we've talked about. It's just putting fancy names on things. So basically, if we have a sequence like this, we can still compare the degrees, and we can see that the output is 3. If the limit exists, it's considered convergent. If the limit does not exist, it's considered divergent, and that's something that will be discussed in later classes. So this would be a convergent limit. This here just puts a function to it rather than a sequence. Okay, so everything is the exact same. So looking at something like this, the function themselves look a little intimidating, but anytime you see an infinity, this is when you want to identify if there is a horizontal asymptote. Because horizontal asymptotes are often referred to as end behaviors of the graph, or end behavior asymptotes. And so if n gets bigger and bigger and bigger and approaches infinity, that is also the end behavior. So compare these. They are the same. Since they're the same, in your mind, you can cancel out the n cubes, and you're just left with a ratio of -6/1. So the limit is -6. Compare these. Okay, if I want to reduce this, -n²/5n³, you can see that this reduces to -1/n. Okay, so as n gets bigger and bigger and bigger, it doesn't matter what value this is. No matter what, this is still approaching 0. Because if the denominator of a fraction gets bigger, so this is bigger, the end behavior is 0. Now this one here is a little bit different. You can think of this as 3 to the power of n over 4 to the power of n. So if we plug in bigger and bigger and bigger numbers, the denominator is going to increase faster because it's bigger. And if you want to write down a few of these terms, you can. If you plug in 1, you have 3/4. If you plug in 2, 9/16, 27/64. And these are just plugging in whole numbers, but you can see what's happening. The denominator is increasing faster than the numerator. So if that's the case, then this limit is 0. More of the same thing. Let's look at the reciprocal of what we just had. So now I have 4 to the nth over 3 to the nth. Well, now the larger number is in the numerator. So now the numerator is bigger and increasing faster as n approaches infinity. So this will approach positive infinity, so the limit does not exist. And if you want to write some of these down, just like we did before, it's just the reciprocal of the previous problem. So you can see that this number is getting bigger and bigger and bigger. Now number 12 looks like a total hot mess, doesn't it? But we're just going to apply some algebra and clean it up a little bit. So when we do that, I'm going to multiply these two fractions across the top and across the bottom, and I'm going to clean this up a little bit. Okay, so this becomes n squared plus n on the top, so just distributing, all over 2n squared. And then don't forget this plus 3 over here. Okay, well, I'm going to use the heart method and rewrite this. So just separating them into two separate fractions gives me n squared over 2n squared plus n over 2n squared plus that 3 on the outside. Well, looking at this, these cancel out and these cancel out. So if I were to write this one more time, I end up with 1/2 plus 1 over 2n plus 3. Let's think about what happens. Now remember, anytime you have multiple terms, you basically take the limit of each piece. Well, the limit of a constant is a constant. So we know this is 1/2. Now if you plug in infinity here, like in your mind, what's happening? Well, this denominator is getting bigger and bigger and bigger and bigger. So this fraction itself is getting smaller and smaller and smaller and smaller. So this is approaching 0. And then lastly, a limit of a constant is a constant. So this is equal to 3.5, which is the same thing as 7/2. So we found the limit of this whole thing as x approaches, or n in this case, as n approaches infinity, is 7/2. That concludes all of the videos for this course. Congratulations.